Pop quiz. In space, there's nothing to push against, yet the rocket moves. How can that happen? Lock in your answer. We'll solve it when we uncover the real physics behind rocket motion. In this video, you'll learn what linear momentum is and how it's conserved in collisions, the same idea that explains how rockets move. We'll build the model, work through examples, clear up a misconception, and finish with a guided rocket problem. Here's the big idea. Linear momentum, denoted with P, is equal to mass times velocity. It's a vector quantity, so direction matters. Double the mass or the speed, and you double the momentum. Reverse the direction, and the momentum reverses too. When no net external force acts, total momentum stays constant. Pushes inside the system can move momentum around, but the overall total never changes. Let's try a sticky collision. A 2-kilogram cart moving right at 3 meters per second hits and sticks to a 1-kilogram cart at rest. Before impact, the total momentum is 6 kilogram meters per second to the right. Afterward, the 3-kilogram combined mass moves at 2 meters per second, keeping the total momentum unchanged. Here's a quick checkpoint. Momentum isn't force. Force only changes momentum. Direction matters. You can't ignore it. And always define your system before using conservation. You've now got the core ideas, the definition, the conservation rule, and a clear example. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Now, let's apply the same momentum rule to rockets. Treat the rocket and the hot exhaust as one isolated system. With no significant external force, the total momentum stays constant, even as mass shifts from the rocket into the exhaust. Time to reveal the answer to our pop quiz. The correct answer is B. Rockets don't create momentum from nothing. The rocket gains forward momentum while the exhaust gains an equal and opposite momentum backward, keeping the total unchanged. Let's calculate one short burst in space. At first, the rocket and fuel together have a total mass of 52 kilograms and are at rest. It ejects 2 kilograms of gas at 500 meters per second backward, relative to the rocket. To keep the total momentum at 0, we write 0 equals 50 mu plus 2 times mu minus 500, which gives mu about 19.2 meters per second upward for the rocket. Momentum stays balanced. What the exhaust takes one way, the rocket takes the other. Watch out for some common pitfalls. Rockets work in a vacuum because the exhaust pushes on the rocket, not on the air. Exhaust speed is often given relative to the rocket, but momentum conservation uses speeds measured relative to an outside frame, like the surrounding space. Near planets, gravity and drag act as external forces, so momentum isn't conserved unless you include them in your system. Now let's recap. Momentum is mass times velocity, a vector with both size and direction. In an isolated system, total momentum stays the same before and after. Rockets move because the exhaust takes equal and opposite momentum the other way. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.